Welcome. The purpose of this video is to explain how PERT networks work within the context of project management. First thing, PERT is yet another way to calculate a CPM network or a critical path network. The difference with PERT is it enables us to configure our project in such a way that it allows for variation. So in the case where you might not know exactly how long a particular task might take, we can allow a shortest possible time, and then a longest possible time, and then sort of a medium time. This difference, this ability to enable variance in project completion, is the big difference between the CPM network and the PERT network. So please keep in mind that the PERT network enables us to have variance in the activities, and then because we allow the variance in the activities, we are able to predict an expected completion time based on the normal probability properties. Now, a couple things to keep in mind. First is these times that we're going to talk about here in a second follow what's called a beta distribution, which enables us to assume we're considering 6 standard deviations. So this is important because with this, we are able then, like I said before, to predict completion times. So let's just make a couple of notes here on what might be important. So you can see here I put some notes that the PERT terms that we need to be aware of, and basically why do we care about this, that the PERT network considers variation and enables us to predict the completion time of a project. And then we also know that with the PERT diagram, it follows a beta distribution, which means that our activity times will be plus or minus 3 standard deviations from the mean. Now you'll note that the second one I put in red. I only did that because it was sort of close on the page, and I was trying to distinguish between the variance in the project and the definition for the beta distribution. Now, in every one of our activities, we're going to know the optimistic, the pessimistic, and the most likely time. So when we calculate this known optimistic time, this is going to be the time that if everything goes really well, we're going to have this time. So this is all possible things go right. And the pessimistic, probably more likely to happen. This is when, you know, everything goes wrong. And then last is the time that it normally takes, kind of on average, it takes this long. So we have to know these 3 times when we do our PERT diagram. With that, we are able to then calculate the expected time and variance for each activity. So when we did the CPM chart, the expected time, this term right here, it was given to us as the time. And it's the number that we put in the activity on node diagram underneath the activity. So in this model, we have to calculate the expected time, and it is this time that we're going to put underneath the activity in the node. So I'm just going to put a node over here on the side, and I'm going to fill this in for us so that you can see what I'm talking about exactly here. So as you can see right over here, I drew out what I'm talking about, just so everybody understands. So when we do the PERT diagram, this is for the PERT, we're using the same activity on node process. This is still going to be early start and early finish, F, and late start and late finish. The only thing that's going to differ is right here. time, I've crossed that out. It's still going to be a time, but we're going to use the expected time in that box. Everything else will be the same. And also, as a part of this, we're going to calculate the expected variance. Now, the expected variance is going to be about how much variation we expect on either side of the time. And I'm going to show you how to calculate that on the next page. So we're going to just put that on hold, except for just to say that variance, remember the symbol for variance is this. And the way we calculate it, in this case, is going to be the difference between b minus a over 6 squared. Now, the project variance and standard deviation, this is going to be calculated as the sum of the critical path items, critical path activities, I guess we'll say, variances. So sum of the critical path activities variances, and then we'll apply that a formula to that. We'll take the square root of that, and that's going to give us the project standard deviation. By summing all of this, the sum of the critical path activities, this will be the project variance. So we put that like this, and then when we take the square root of the project variance, we're going to get the project standard deviation, which is ultimately what we're after. Then, computing the probability of project completion in a particular time, we're going to use a z calculation to do this. We're going to say z will equal the expected project completion and actually we're going to write it like this instead. Z will equal the due date, whatever date we want it to be done, minus the expected project completion date divided by the path standard deviation. So like that. Now, maybe some of this might be new terms to you, but we're going to go over it all, and hopefully it will all make lots of sense. So here we are with our project, and we're going to calculate these things that I was just talking about right here. So the first thing we're going to do here is for A, we're going to calculate its expected time. So you can see I just wrote out here the expected time for A is going to be 1 plus 4 times 2 times 3. And I just used this formula right here. So A is here, M is here, and B is here. So a couple questions I often get on this is the 4 right here. Is this always 4? And yes, indeed, it is always 4. It doesn't change. It's a constant in this equation. And this 6 right here is also a constant. And just so you know why the 6 exists or why it's there, it's because we're only considering 6 standard deviations from the mean. And the reason why it's a 4 is because we need this middle this middle time to have about 4 times the weight of the optimistic and the pessimistic time. So each of them, like this one has the weight of 1, this one has the weight of, A has the weight of 1, B has the weight of 1, and M has the weight of 4, is essentially the way to think about it. So here's our formula that we've got, and when we calculate this in our calculator, we should get 2 as the answer. So our expected time for activity A is 2. So, and you'll see that in this case it is the same as the this M time, as is sometimes the case. It isn't always the case, but sometimes it is. So in this case it is. So then we're going to go on and compute the expected time for activity number B there, we'll do it exactly the same way that we just did. DE is going to be 2 plus 4 times 3 plus 4 divided by 6 should be about 3. And again, in this case, it's the same as the 3 here. And then I'm going to do one more for you, and then I'll move over to the variance. So that expected time for activity C now was going to be 1 plus 2, 4 times 2. 4 times 2 plus 3 divided by 6, which is also going to be 2 because it's exactly the same as this one here. And also the number is 2, the expected time. Let's take a look over here at the variance. So remember, this is the amount of variation we expect to see in any particular activity. We're going to take the high minus the low. We're going to divide it by 6 because you know we've got the 6 standard deviations, and we're going to square it. So in this first one, we're going to take 3 minus 1, and we're going to divide that by 6 and square it. And this is going to, actually I need to scoot this over. So we got essentially 2 over 6 squared, right? Which is really the same as 1 over 3 squared, which is really the same as 1 over 9, and 1/9, the decimal conversion then is 0.111. And I wrote all this out just to sort of show you. You can do it by hand, you can just stick it in your calculator, but you should write enough information here that you can follow it. So I'm going to reduce this down, but I just wanted to show you how I got it. And then I went ahead and did the second one. It's the same thing. We still end up with 2 over 6, which is still 0.11, 1. And then this third one here, of course, is exactly the same because it's the same number, so we don't really need to write that out. We know it's going to be 0.111. And I'm going to fill in these numbers, and I think it'd be a good idea if you just pause this video now and filled it in yourself, and then you can just check them back against mine. A lot of this, like many things, it's not so much about getting the right answer. I assume you're going to get the right answer, but it's interpreting it. So when I come back on, I'll talk a little bit about what each of these numbers mean. Okay, so now you can see from my drawing here are the numbers. Some of them I've written all the way out, and some of them I've kind of done it quickly. But now the next step we're going to do is to draw out our drawing, because what these numbers tell us is the most likely time, or the expected time, as to use the terms from the text here, the expected time that each of these tasks is going to take. Right, so these are the numbers that we want to use, those ones I just circled in green. And we're going to use those. We're going to set up our diagram. We're going to follow this precedence chart just like we always have. And I'm going to draw it right here below. Right, it's the same process as before, except now we have slightly different numbers. But first thing we had to do was calculate this expected time. So this over here, this would be kind of step 1. We had to also calculate the variance, although we don't necessarily need to use it just yet, but we will. And then the third step is going to be down here, and this is going to be to draw our critical path network. So we're going to start with a start here, and we notice that both B and C require no immediate predecessor, so we'll just draw them here real quick. A and B, and I think I just said B and C, but I meant to say A and B have no immediate predecessor. We'll put those there, and we'll connect them with an arrow. So I've got A and B drawn. Now I'm going to go on to draw C, and we notice that C must come after A, and then D must come after both A and B. So let me put them on. So there I've drawn C and D, and let's go up here and take a look at E and F. Both need to follow C, so we can put them on here. E and F, both following C, and then we got G that needs to follow D and E. So you can see I've drawn on the rest of the activities, just easier because I kept having to switch back and forth, but let me just go through it. I've got C here, which is I think where I left off, and then I went ahead to draw D, because D comes after C in the alphabet. So here's D down here, and it has to be connected to both A and B, so we've got that. And then we've got E and F, and I reversed these again just like I did in class because I knew that it was just going to be easier to draw it. So F is on top, and F, you notice I have this one in pink, and that's because the F time is different. Before it was 3, but now it's 2. So I have that on there. And then G, you'll notice, is the one also that had changed just like F. So I got that in pink. And then H needs to be preceded by both F and G. And then over here I've got the end. Here's the start. So if we do the forward pass, you're going to notice it's the same diagram as the problem we had worked together in class, problem 3.1. So if you're pretty clear on how to do the critical path network, you probably don't need to watch this part of the video. You can probably skip forward by about a minute, and it'll all be filled in. But if you've got some question about it, then you probably want to watch this. I'm going to go through it quickly. So A, the earliest it could start is 0. It takes 2 units of time, so it ends at 2. C, the earliest it can start is 2. Takes 2 units of time, so it will finish at 4. While we're on A, we need to go down to B and D. So B can start at 0, end at 3. D, same thing. We have to consider this 3 and this 2. We take the larger of the 2 on the forward pass. 3 plus 4 is 7. So now we're set there. Go back up here to C. C, we're going to carry over to F with the 4, the earliest finish of C, and then we're going to add 2 to that. That makes this 6 here, which is different than the previous way we had done this. And then we're going to bring this 4 down here, and 4 plus 4 will be 8. And G now, we got a choice of starting it at 8 or 7, but because we need the longer of the time, we're going to put 8 here. 8 plus 4 is going to be 12. And then when we go into H here, we're going to have either 6 right here or 12. So we're going to pick 12 because we know that 12 is, we got to pick the higher of the two. So 12 plus 2 is then going to be 14. So we're going to put that up here. The CP time will equal 14, and we're going to also write it down here because we're going to do the backwards pass. We're going to do that in a different color because it just makes it easier to see it. So we'll write it right here in the different color, 14 weeks. So this will go to here. 14 minus 2 is going to be 12. We're going to take this. Remember, this is the late start time, and the late start time of an activity goes back to the immediate predecessor, so that's going to be F and to G, and that is going to be their latest finish time. So F must be done by 12 and G needs to be done by 12. So G, in order for it to be done by 12, it's going to have to start by 8, which means there's no slack here, so it must be on the critical path. So we'll go ahead and highlight that. And H also has no slack, so it is also on the critical path. So now we take our 8 here, and we're going to bring that over here to E. And 8 minus 4 is going to be 4, which is going to have to go up here to C, 4. However, I kind of jumped the gun there because we're doing a backwards pass, and remember, this is designated by the late start, and so the late start of the one that follows after will be the late finish of the predecessor. However, in this case we got a 4 and we have a 10 here, and because we're doing the backwards pass, we need to take the shorter of the times, and so that's what we did. We took the shorter of the times, but I did jump the gun. We're going to take this 4, it's going to go to here. So from G we go back over here to D, and we see that G's latest start time is 8, so that means that on D the latest finish time will be 8, and then 8 minus 4 is going to be 4, so we can see we've got some slack there of 1. And then we're going to go up here for C. We take our 4 up, we bring it to here. 4 minus 2 is 2, so we can see that E is on the critical path, as is C. So we'll go ahead and circle those on our trusty green marker here. And then we also know that we're going to go back over here to A. So A needs to be done by 2. 2 minus 2 is 0. So that's going to be our last activity on the critical path. And we can go on down here to D. We just did that one, but we can go over here to B. We've got B can be done as late as 4. 4 minus 3 is going to be 1. So we've got more slack there. So let's make some notes. We've got our critical path here. It's going to be A dash C dash E dash G dash H, and the time is going to be 14 weeks. So expected project completion time, we're going to have 14 weeks. And then the project variance. So here we've got to go back up here, and we need to note on our diagram which activities are on the critical path. So we'll do that using the green here. We've got A, so we'll just do this box. We've got C, we've got E, we've got G, and we have H. So these we need to add up in order to compute our project standard deviation. So first thing we have to do is add up those path variances. So we'll do that with our pen here instead of our highlighter. So we've got to add A, which is 0.111, plus C, which is 0.111, plus E, which is 1, plus F, plus G, which is 1.778, plus H, which is 0.111. So if we add up all these in our calculator, we're going to get 3.111, and I've got this noted as the sum of the critical path variances, which is going to be 3.111. From there, I want to create this project standard deviation, so all I need to do is take the square root of the critical path variance. So I'm just going to take the square root of 3.111, which will be 1.764. So this is the amount we expect our project to vary by. So now we're going to compute the z value for expected project completion in 15.764 weeks. So let me just write that down here. So we're going to calculate the probability that this project's going to be done in, like I said, 15.764 weeks. You can see it right there. And I'm going to calculate it over here. And once I get it calculated, I'm going to draw it out for you and explain why it is this. But let me just show you here. Z is going to be 15.764 minus 14 divided by 1.764, which is going to equal 1.764 divided by 1.764, which is going to equal 1. So now we need to interpret what that 1 means. So I'm going to go to the next page and draw it out for you. Ostensibly, what it is going to tell us is that we have an 84% chance not change, chance, or less, well, actually I should say an 84% chance of completing this project in 15.764 weeks or less. But let's go ahead onto this next page and I'll show you why that is the case. So now we're going to interpret what we just found on the previous page. Okay, so this is a concept that applies to the normal distribution. It's very important. It comes up many times in this class. If you're relatively familiar with it, this will be enough for you to, this will make enough sense for you. So what I'm going to start with is you're looking at a normal distribution that's got some key identifiers on it. So we're going to start with mu here, and we're going to note that mu is the mean, always, it's always the mean. But for our project, remember we just did our project, we found our mean to be 14 weeks. On average, we expect our project to take 14 weeks. We also learned that our project's standard deviation, so that is this space right here that is in blue, that's kind of hard to see. Each of these, one standard deviation always takes up 34%, but in our case, it has the value of 1.764, and over here 1.764. So what this tells us is our project 68% of the time will be completed between 12.236 weeks and 15.76 weeks. And that is because when something follows the normal distribution, we know that 68% of the time all of the observations fall within one plus or minus one standard deviation. And so in our case, that's what this is depicting. Now my question that I had asked on the previous page was, what is the chances that the project will be done in 15.76 weeks or less? So a couple things about this normal distribution, just to sort of refresh your memory, is that it always adds up to 100%. So this whole thing here is always going to be equal to 100%. So that means that half of it, either this half or this half, is always going to be 50%. Remember, this is frequency of something occurring. So in my case, I asked exactly plus one standard deviation, and I gave you the answer that said it's going to happen. The probability would be 84% of the project being done in 15.76 weeks or less. So where did I get that from? Well, I took this amount right here, which is 34%, and I added it to this amount over here, which is 50%. So 50 plus 34 is 84. Now, most people don't necessarily have the z-chart in their minds, so I'm going to show you how you can get that from looking at the z-chart as well. But let's go ahead and put the calculation here. We've got the z will equal the due date, or the date that they're giving you in the problem, minus the expected completion. And we're going to divide that by the path standard deviation, which we annotate like this. And so that's going to equal 15.764 minus 14 divided by 1.764, which, remember, it equaled 1.764 divided by 1.764, which is of course 1. So essentially what we have here is z equal to 1. So now we're going to go look at our z-chart, which is on the previous page. So I've put the z-chart here so we can look at it all in one. And I've noted up here that that little thing that it's hard to see is a z. And so what we do is we take our z number here and we go find it on this column. So we're going to come straight down here until we get to 1. In our case, it's easy because it's 1. So we don't need to look any further than just to 1 here. So we'll go to 1. And we'll see that it's 0.8413. which is basically 84% chance that the project will be completed in 15.764 weeks or less. Now, let's go ahead and change that from 15.764 to, let's just say 16. So we're going to have z will equal 16 minus 14 divided by 1.764, which is essentially 2 divided by 1.764, which will equal 1.134. So now we're going to go over here and we're going to take a look and find our z value on here. Same thing, we're going to come down the column on the left till we get to 1.13. So we got 1.1 right there. But we need to go over to where we have 0.3, which is right there. So we want to come down this column here till we find the intersection of these two things, which is right there, and it's 87%, 8708. So we're going to go like this and say 0.8708, or about 87% chance that this project would be complete in 16 weeks or less. And that's because we're talking about this project finishing about right here, probably on this thing, a little bit beyond our other point, and all the way back to the origin. Now, sometimes students find this part confusing, but it's important for me to start explaining this to you now as well. If I was to ask the same exact question, except for to say, what is the chances that this project would be completed in 16 weeks or more, now we have the same exact calculation, but we need to do one extra step. So first thing I want to do is just sort of clarify, this is project complete in 16 weeks or less. And then over here, I'm going to do it in pink also so that you know it's different. We're going to do project complete in 16 weeks or more. So now we still calculate everything the same, right? We still have our z value. We've got our z equal to 1.134. We look it up, we still get 0.8708. But now, because I have asked you not the chances of the project being complete in 16 weeks or less, the green part here, I'm now asking you for the chances of it being done in 16 weeks or more. So now I want to know this part over here, this pink part. Well, we know it's if half of this thing from here over to here is 50%, and we've already chunked off more than 34%, well, our value is going to go way down. So what we need to do in order to figure this out, we have to do 1 minus 0.8708, which is about 0.129, or about 13%. So it's about a 13% chance that the project would finish in 16 weeks or more, while it's about an 87% chance it would finish in 16 weeks or less. So we're going to write in here 13%, and over here we're going to write in blue 87%. So I hope this is clear, and for homework you really need to do the other problem in this packet, which is handout problem 3.4. And then there are also 4 homework problems. Didn't want to misspeak, so I thought I'd just flip back here. So we just did this problem here, 3.3, and then for homework, you're going to want to work this one, 3.4. Now, it could very well be that we've already worked this in class, and so this is just a review for you, but you can always download a blank sheet of this and redo it, because a little practice is probably really worth its weight in gold. And then these are the homework problems that you need to practice. Okay, 313, 314, 317, 321. All of those problems will help sort of reinforce this whole idea. So, I really hope this is helpful. Please refer to it as necessary, and please ask me questions if you don't understand something. All right, take care.